Okay, good morning. My name's Elliot. For some strange reason, everybody calls me EHO, so that comes off the thing. It's interesting, I have apparently an illegal email address at Microsoft. They don't allow initials, but somehow my boss arranged to get that set up, so now you know how to get a hold of me. I can't see my slides on the monitors down here.
We'll fix it.
Okay, alrighty. So I'll have to look up here. Truth in advertising. Everything you ever wanted to know about threading? Probably not. I thought it was a cute title. But we'll try to go as deep as we can and kind of tell the story of threading, multi-threading, UI, threading, and those kinds of things. Thank you for the monitor. Circa 2013. So I'll try to give you the best survey I can in 1 hour about what the system looks like for that thing. C++ guru, I'm not your guy. I see a lot of these people in the front row. We're the people who look at C++ 11 and 14 and then say, oh yeah, I'm going to learn about X and then implement that. So we really appreciate that work. And when we finally get a compiler in Windows that does variadic templates, we are going to be so happy. Oh, where's my phone? The speaker bios and the intro for this had an interesting thing in it, which said that it was going to be dry this year and relatively warm. And for those of you who are watching on the web from someplace else, we had a fantastic lightning storm and a deluge of rain last night. So it's rarely warm enough and wet enough here for us to have lightning. So we were actually pretty enthused last night. So sorry it rained on you last night, but we thought that kind of lightning storm's really, really exciting. I watched some of the other talks in this conference and saw interesting slides with Atari computers on them and cats and dragons, and I'm going, man, my slide deck is just not up to snuff here. So I'm sorry to say, no dragons, only cats. Okay, so what are we going to talk about? So we're going to go through a short history of threading in Windows. Actually, that's one slide. Talk about how threading works in the Windows runtime and the desktop, actually, because we'll be going into user mode thread pool, how the kernel schedules things. And then we're going to spend a bunch of time talking about threading and UI programming and how that's evolved over the last 5 to 8 years. And like, if you've been programming on Windows or actually in any modern system, the way you program the lower levels of your app and the UI has really changed a lot in the last few years. So we'll talk about how we've gone through that evolution on the Windows side and the things that you will be careful of and how we view that system circa Windows 8 and 8.1. And then we'll also talk about the async and the async pattern in Windows. Well, actually, async pattern in WinRT and how that fits back together into those other two topics. So I see some people who are maybe as advanced in age as I am. And so if you go back, you can remember we had programs and systems that had a single thread of execution. And so when begin thread EX appeared in VC10 or whatever it was back then in the mid-90s, it was like this new concept, just like multi-threading. What's that? Because we actually always did something on one thread of execution and then yielded. And so you had to be very cooperative for the system to work at all. And it was really easy to get your program into these compute-intensive loops and not do anything interesting at all. And so once we did this and we shipped NT and then integrated the NT kernel into one version of Windows, then people started to use the threads. And then what we ended up with the explosions of threads in Windows programs, which for better or for worse created a lot of functionality, but also created a lot of things that would use the CPU and occasionally deadlock. rather than have lots and lots of threads that you had to individually manage, the first thing people started doing was writing their own thread pools so that they could create units of work and then manage a few fewer threads and then get their program a little bit better under control. And so we'll go through a little bit about the thread pool in some of these slides, but the message there is that we want to think about our programs in terms of units of work rather than threads of execution, because it'll create a lot of benefits, what we'll go through in more detail. So, what's a thread pool? At its most basic form, a thread pool is a really simple thing. It's a queue which contains work. It has n threads to peel that work off of the queue and execute it, and some algorithm that does that. What's not simple is the actual implementation of a thread pool, because once you get this very, very simple thing, which everybody in the room can write in one afternoon, then you actually have to deploy it and then throw work queues at that. And then what you end up finding is, even in your one program, you end up with a really diverse set of work, and that diverse set of work, which runs multiple jobs, talking to lots of resources and having to deal with locking, ends up with a lot of interesting patterns. And so once you do this, then you actually have to tune and debug and fix that thing. So the first decision you have after you get a simple QDQ algorithm for that is, how many threads do you have? Well, the most obvious thing to do in that thing is have one thread per core. And that's actually fine until you do anything that blocks. And so if you have I/O or any type of contention on an I/O on an event or a semaphore, then you have a really bad problem there, because that thread's going to block, and then you need some other threads. And so that busy thread can't do any additional work for you. And so you end up having to decide, okay, now I need to be able to create threads, put them in the pool, and then deploy those threads for that thing. And so you end up with an algorithm where you need a greater number of threads than the number of cores. And then obviously at some point you have to have set up a limit so you don't explode threads. So once you get into this kind of setup, then you need, for your internal implementation, to be able to manage a bunch of states of those work items. And so the most obvious one is if you have thread pool type for work. So I have a unit of work that I'm going to do in a lambda or a function or a functor, and then I'm going to do that. The first thing that many work items will attempt to do is access a resource which is not available. So one of those things can immediately get into a wait state while they're waiting for some resource to become available, or they'll do I/O, and then they'll need to block and wait for that I/O to complete, or they're actually timed, and you have to wait for the timer to fire, et cetera. So you can create all of these sorts of things. But these are the ways that the work gets executed and triggered. And so you have to set up these things so that the work will execute at the correct time and make the most efficient use of the threads that you have in the pool. I want to go through one of the examples that we experienced when we went through and rebuilt the thread pool implementation in the kind of the Vista timeframe. And so one of the examples that we have is that we had a web server servicing web requests. And so the way this typically works is you will have n worker threads servicing the incoming request. I want to get to defaulted HTML or index.html. And then you have one or more worker threads that will read the actual HTML file off of disk and into cache. And one of the things that we actually encountered was very simple program errors can lead to very disastrous results. Here, we have one simple queue. Now, one thing it should be apparent is you're going to have priority levels on these things. And so you will usually have multiple queues per priority level. But this example is very simplistic. And so you have a series of work items here, and then you have one or more threads executing those work items. And then it turns out that all of the current work items are blocked on a web page read. And so all of these work items are in the block state, or TP wait, and basically we need to create another thread or get another thread out of the queue to enable to service the inevitable incoming read from another client request. However, there's a really bad bug in this code that says the work item here is still in the queue, and it's the one that reads the web page, and will actually resolve this deadlock. So this is obviously a really bad programming error, okay? And then, so the term we have for this is popular internal dependency. So there's going to be a lot more work created. The work's going to come in. It's going to try to read the web page, which is not yet in cache, and then it will block. And so you can see what the inevitable result is here. We're going to create another thread, which is immediately going to block on that internal dependency. And so you can see what's going to happen in this thread pool thing is we're just going to keep on creating threads. Excuse me, there we go. And this is one of the patterns that creates thread explosions. And so you can see that the simplistic algorithm that says, I'll just go get another thread to service that next piece of work can go really, really bad and wrong on you very, very quickly. And so we just call this kind of problem thread explosion. And so this is just one of the patterns that can do that. There's another variation of this pattern called popular external dependency, where actually that work item or that thing that's actually going to resolve the deadlock and set the event on that event handle is actually not in the queue. So it's just external, but it's the same bad problem, right? So you're going to explode the threads. And when we first deployed this, so in this time frame, we actually saw variations of this problem, and so had to figure out how to deal with this. Question?
Why does it never make any progress, though? You think that work item would eventually get to read the page. What is it waiting? The one that's trying to read the
Yeah, so I mean, the thing that I think I talk about in a following slide is that this may eventually resolve. Okay, so let's say that the work item that's circled in red will actually resolve and get popped off. Meantime, however, before it got done, we created 1,000 threads. And so there's three possible outcomes. Is you resolve the wait quickly and you don't have a problem. The second thing is you don't resolve the wait quickly and then you explode 1,000 threads before you get that, and then you have to deal with all of the overhead of returning those threads to the operating system, or suffering sitting around with too many threads in your thread pool. The third thing is that thing never comes off and you deadlock, or at least you deadlock that part of the program. And so so the goal here is we want to resolve this dependency or fail into the deadlock state quickly without creating 1,000 threads. So that's really the goal here. Okay, so another example where we saw this problem was GC. So what does a garbage collector do? It will occasionally decide that it needs to collect objects in the memory. So it will have to walk the graph of all the objects, find out which ones have no references, and mark them as candidates for collection, and then eventually collect them. So it's a really simplistic garbage collection algorithm. So what do they have to do? You can't execute those objects while the garbage collection is happening. So you have to freeze all the threads in the program. And it turns out that freezing the threads in the program, which may be only partially managed under the garbage collector, also causes kind of thread explosion. And so there are many, many different ways to get you into this problem. So the way that we resolve this problem was kind of two-part. And I have to apologize because we did actually end up using a heuristic. So there's two elements to this. One is to be able to observe the problem state. And so what the problem state is you're continuing to dequeue work items that immediately block on the same thing. It turns out that in order to observe that, you have to be in the kernel because the kernel has the global state of all of the objects. And so one of the messages I want to tell you on the thread pool is it's very, very hard to deal with certain types of problems in thread pools without having a global view of the system. Fortunately, inside the OS, with the kernel, you actually have that global view. So you can detect popular internal and external dependencies because you know that there's the system entity, which is the event handle, that is blocking on this thing. And you can observe people continuing to block on the same thing. If we observe this popular internal or external dependency, then what we do is we start putting delays on the creation of the next thread. And so basically what we do is we slow the thread pool down. So in the beginning, the delay is only very, very short, right? Because we don't know what the volume of things that are incoming that will cause us to create the second and the third and the fourth additional thread. And so what happens is that thing. So in the case of the questioner, if that work item pops out of the queue and gets resolved, then of course everybody's going to release, and then the world's a happy place. If it doesn't, then what happens is the delay gets a little bit longer, and then we just get a little bit slower and slower and slower in creating this thing. And so one of two things, until we hit a limit, of course. So one of two things will happen. Either the internal dependency will resolve, and then you've made progress without creating too many threads, or it never resolves, and you kind of just slowly accrete threads in the system without actually exploding. Of course, the best way to do this is to make sure you do the thing. You know, in this case, the web page read should be on a high priority work item and resolve quickly. And so the thing about this is, but the thing about the thread pools is you will see buggy workloads come into the thread pool. And so we have to deal with a diverse set of workloads, including the ones that have bugs. Okay, so the other thing you have to deal with besides getting the work run and not exploding a lot of resources while you're doing it is fairly running work, okay? So in any of these systems, you're going to create priorities for these things. So, you know, the simplest possible system has 3 levels, high, medium, and low. And so you want to create the ability for work to run according to those priority levels in some order, typically FIFO. So the issue that we ran into is once you have work that's blocked, you eventually want to run that work when it unblocks. So an event will get signaled, or I/O will complete, and then you want to run those work items. And so we have a really highly efficient mechanism in the OS called I/O completion ports. And so we know when an I/O is completed, and then we also use that for knowing when an event will resolve. And so the kernel will immediately know when something's ready to run, and then it can release that to be able to run. So when it's ready to run, we call that a ready thread. And then when the thread actually runs, then we call that a C switch. So it context switches in, and then the thread runs. However, in Windows 7, TP work always trumped TP IO and TP wait. So what happened was TP work would run, and only when TP work was fully drained would TPIO and TP waits be able to run in the system. And so basically what we had in that generation was an unfair system. And so work items could starve things that ended up with execution triggers of TPIO and TP wait. And so even though you thought you had created a fair system with work levels, it turns out once you have different kinds of execution triggers, you have to be able to merge those back into the work queues and get them executed in a fair way. And so that kind of blending is also, it turns out, a function of being able to view the system through kernel mode. Because once these IRPs, or these interrupt request packets, complete and come back, we have to be able to merge the work. So what does this look like? Let me describe the diagram here. So the line is the ring transition line. So above the line is user mode, and below the line is kernel mode. And so the way this is structured now is you have a worker thread factory in kernel mode. So basically, the entity that is responsible for creating the threads for the thread pool is actually sitting in the kernel. And it knows how to execute or release those threads to run for various kinds of work, I/O, or things that have become unblocked because an event has gotten signaled. And so there will be some N of those things. And then the user mode side is actually responsible for queue management. And so what they will do is work items will be queued, a worker thread will come from the factory, and then it will be executed. Now, that's good if you just have regular work items. They're going to do some sort of computation in that workload. But eventually, you will have execution triggers for I/O and wait and timers, and then those IRPs will complete. And so what happens is that the kernel, which is responsible for the threads, will know that these items released and became available to run. And then they will be transported up to the user mode queue and released and start running. And so one of the things that you should be able to observe here if you study the system is that many of these will complete simultaneously over a short unit of time. I mean, we actually measure and calculate performance at the kernel level in nanoseconds. And so once you start thinking about this in terms of scheduling work in milliseconds there, you can realize that at the level where the IRPs are completing, many of them will complete in a very short period of time. So you could have many of them, in the low tens of them, complete per millisecond. And so what happens is you want to make sure that when you make the transition from the worker thread factory up into the user mode queues, that you do that in batches. Okay? And what that does is it minimizes the ring transitions so that you can transport a lot of work, merge them into the queues fairly so that they get executed at the appropriate fairness level according to whatever priority queue those items are queued into. So I think that I covered the information in this slide. There's two key points on this slide. Number one is it's very difficult on thread pools to balance throughput, resources, and fairness in user mode only. So there are a bunch of very smart people in here. You could write these things, and you could put a lot of custom tweaks for your workload into these things. But there are many things because your application process that your code is executing in does not have a global view of the system, cannot possibly do. And so this is not like because you're not good programmers, it's because you don't have a position in the system where you can observe these kinds of things happening. And so, sorry to take such a deep dive into OS kernel things, but with C++, why do you care, in terms of going native? So the reason that you care is when you have your unique asset, that snowflake that you built, that you drop onto the world, you really need to think about that, not in threads of execution, but units of work. It's like whether it's on Windows with our thread pool or on iOS with Grand Central Dispatch, you really need to think about how you structure your library and your value add to the world in terms of work, because you really want to run these in terms of work units and not threads. And so even though I wanted to talk to you about threads, really one of my key messages is to think about how to do your value add in terms of units of work. On the desktop, which most of you have most of your experience in, you have create thread. Like you can create thread, dedicated long-running threads, and dedicate work to them. On WinRT, we made the decision that you don't have create thread. So you must use a thread pool only on WinRT things. And you can imagine that when we made this decision internally in Windows 8, that everybody clapped and said, oh yeah, that's fine. No, there was a huge controversy about this internally about whether or not in the new platform you should be able to create threads. And after a lot of debate, not much of which I was involved in, but there was a decision that create thread is not allowed to be called in the modern platform. So this is where you throw tomatoes at me. And the reason you throw tomatoes at me is you say, I need a dedicated thread that I control. And it turns out that there are actually workloads that benefit greatly from one continuous thread that doesn't go away, that continuously works on something. And so games, when they're laying out off-screen parts of the board, make use of this technique. And also any other thing that's doing off-screen layout kinds of things. So if you have viewports kinds of algorithms that you're doing. And so basically, this is the mantra that is, I have long-running work. So we actually didn't leave you out high and dry. So the thread pool has a mode we call time sliced. Basically, the traditional thread pool is batch. So you have like batches of work that will get serviced over unit periods of time so that you can do this. And basically, so we have this dedicated thread model called time slice. So I think I have a slide a little bit later that shows you the APIs. One of the options on those APIs is that you want batched or time sliced. So the long-running thread is time slice, but it still comes out of the thread pool. It's still part of the system that is built on top of the kernel knowledge, and so you still get a lot of the benefit that you had before, but you get the benefit of long-running work. And so here's the way you should think about it on time slice versus batch. Excuse me. It's a latency versus throughput model. I mean, when you have units of work, they will execute eventually. And so when you have units of work, they inherently have latency involved in them. You don't know exactly when they will work. You can have high priority, and if the system's not super loaded, it will run pretty quickly. But typically, you don't want to run very many high priority workloads. And I'll talk about the reason why for that in a little bit. You want to run normal or low so that you can get good performance on the system. But if you have these kinds of workloads where you want to run bursts of work immediately, the time slice mode is good. But one last thing I want to say before I plug Pedro's talk is that once a thread is released and running, it's not a special thing just because it came out of the thread pool. It ends up being a regular Windows thread, and every Windows thread is subject to quantum limits. It's only allowed to run for so long, and other threads, whether or not they're in a thread pool, will get scheduled, they'll be ready, and that thing will lose its quantum, get switched out, and another thread will run. So even though you have this dedicated long-running thread that came out of this thread pool with this time-sliced promise, what time-slice means is it's running on a quantum. So it's at the point it comes out of the thread pool and it's running a work, it's just a thread. This portion of the talk is a summary of Pedro's Channel 9 talk with Charles from a few months ago. And if you want to dig into any more level of detail than this, I recommend you look at this talk because he'll talk more about kernel scheduling and those sorts of things. But the key message here is units of work. Here's the APIs and the little snippet of code on what that looks like in WinRT. We're going to get into UI next, because eventually, once you do all this background work, you're going to have to reflect it into the UI. The next topic before we get there is agility. So probably this concept of agile objects is unfamiliar unless you've been programming on the new platform recently. So in WinRT, we've done as much as we possibly to say that objects are objects and threads are threads. And what that means is I don't want you to have to know what an apartment is. So, show of hands here, how many people know what a comm apartment is? Okay, like for the web and the later thing, half the people in the room raised their hands. So I'm actually astounded that that many people actually raised your hands. So this is kind of a seasoned group of people. So let me ask you a different question. How many people want to know what a comm apartment is? Okay, this is great. Okay, 2 people that I could count, it's kind of hard to see up here, raise their hands. That's exactly the correct answer and the goal here. We don't actually want you to know or worry or care what a comm apartment is. Why is that? Well, that's because multi-threading is hard enough without having to worry about another concept that's weird. Right? And that's basically what a comm apartment is this weird thing that adds on to something that's really hard. I mean, multi-threading is really, really hard already. Like you have multi-thread resource contention. You spend your entire life carefully designing locks. If you're lucky, you have one lock, and then you don't have to worry about lock ordering. And then you have to like carefully tune your system, and then you test it, and then you find the deadlocks, right? I mean, it's inevitable. There's no way you can write this kind of system that doesn't suffer from this problem. And it gets more complex. You get more locks. You get more objects. You get more resources, and you spend, some significant part of your time, 25%, like managing your locks and your deadlocks, right? Once you get your system written. So multi-threading is hard enough that we don't want to layer another additional layer of complexity. And so despite, in addition to having to you go into an object, it's got I unknown, you have to QI, you don't know what to QI for. Then after you got to that part of it, the impenetrability of the system, you ended up with, oh, now I have to deal with an apartment. I'm in the right apartment. I'm executing this thing. And so the only context that we or I want you to worry about is the UI context. You can't get away from that. UIs are single-threaded. Objects are thread-defined in UIs. And that's the context we want you to worry about, not this other weird thing about comm apartments. So there's a technique that was invented in comm a long time ago called the free-threaded marshaller, which is a very strange name for it. But what it allows you to do is to create an object that can run in any apartment. And so that's a really incredible thing, because what that does is it makes an object that can be accessed from any thread without you having to worry about, am I in the right apartment? Because it's agile to every apartment. And if you think about a regular C++ object, you can just call it from every thread. There's no special protocol for you to say, oh, can I run on this thread or can I run on this thread? There isn't some protocol. Unless you violate some rule of the UI that does thread checking, you never have to worry about that thing. And so what an agile object in WinRT does is it says, I can go to any apartment and execute correctly. And so almost all of the objects in our system are agile. And so they can be run in any apartment. And so the magic of that little bit is that once they can run in any apartment, then you don't have to worry about apartments, because they can just go there. There are 2 plugs in here. The first one is an MSDN link. The second one is a couple of talks, one that Martin Lovell did, and then a Channel 9 video. So there's a lot more detail there. But actually, you don't need to know any more than what's on this slide is. If the object's agile, you can just treat it as a multi-threaded object. And luckily, agile is the default in the system. There's basically 2 kinds of objects in the new WinRT system: UI-affine ones and agile. And so with very, very few exceptions, you can consult these objects at runtime by QIing them for a new interface called iAgile objects. So they will advertise their ability to do the thing, and it's also described in the metadata. And so there's full view of how you can treat these objects. Okay, so now, once we have these agile objects, guess what? They can be called from the UI. So now let's talk about UI and this new thing we called ASTA. So all mainstream systems, not just Windows, have UIs that are thread-defined. Like if you on iOS call some part of the UI from the wrong thread, what happens? You get an error, right? Same thing on Windows. And so the JavaScript stack just will only execute on one thread, and the XAML stack actually checks every call into it on whether you're running on the correct thread. So whether or not you like it, you're already dealing with one context, and that's the UI context. And you're already very familiar with being careful that you will only ever operate on the UI from the blessed thread, which is the UI thread. And so don't worry about apartments, just worry about the UI context. And you already know how to do that. So once you're dealing with the wonderful, once you're back in the wonderful world of single-threadedness, then you're single-threaded. And so one of the classic problems that we dealt with in the earlier version of like COM UI and Win32 was reentrancy. And reentrancy is this: I'm doing thing A, I call out somewhere while I'm doing thing A, another thing comes in, and all of a sudden I'm doing thing B. This is called surprising reentrancy. And so a tremendous number of the crashes in a very popular piece of Microsoft software, which I will not name, is due to reentrancy. It's because these single-threaded contexts can get re-entered, and then all of a sudden you're doing something you didn't expect to do. And it leads to all sorts of problems, because what happens on a UI thread is like, well, there's only a single thread of execution. I don't need a lock. I'm doing this thing on this thing. It's unlocked, free-threaded. There's only one thread that can ever do this thing. But all of a sudden, another block of your code, which also doesn't have locks, doesn't think it needs locks, starts operating on that same thing. And guess what? You're wedged at that point. Like, you get into this inconsistent state. If you're lucky in these cases, you crash. If you're unlucky, you corrupt the state of the application and you keep running. And those are the worst bugs of all, right? Because the crime happened at time A, and then the really bad thing happens at time B, and all the evidence of what happened at time A is already gone. And then you have to track this back. And so UI has basically two models when you're running on the single thread of execution. You can be reentrant or you can be non-reentrant. The thing about non-reentrancy is if you don't allow that other thing to come in and start executing thing B, guess what? That thing that comes in is blocked. And so you have a choice of reentrancy and surprises or non-reentrancy and potential deadlock. So there is no magic bullet here. It's just a choice you have to make. So how do I deal with this? So let's talk about the cases that matter. So option one talks about you have this background thread. Can it call directly into the object running on the UI thread? Turns out this can be safe, but it's pretty difficult to guarantee that it's safe. The second option is the pattern we call the dispatcher, which says, I'm going to post a notification on that thread, and please get to it when you can. And it turns out that's the model I'm going to recommend for you. It's the guaranteed safe model, but we'll deal with some other issues of what the challenges are on the dispatch model. On the opposite side, can UI threads call out? That's a lot easier to guarantee safety on, especially if you're in a system with non-reentrancy. Because once you call out and you're non-reentrant, you don't have to worry about something coming back in while you're waiting for that call to come back and causing you, a surprise that you're not dealing with. And then the last thing is don't run too long on the UI thread, and that's kind of a mom and apple pie kind of thing. Oops. Sorry. Okay, so every once in a while you get the opportunity to write something 1.0 and new. And so we had that opportunity in Windows 8. A fundamental question you should ask yourself at the very beginning of building these new UI systems with single-threaded UI, which is the only kind of UI systems anybody's ever been able to build, is, do I allow reentrancy? It's almost the very first thing that you have to decide. Next, do you allow arbitrary threading? We talked about that before. And so the last thing is how much synchronous programming do you want to leave in your system? I think many of you have used Windows, and so you've seen the spinning hourglass or the spinning donut. And so you know what the penalty is for screwing up and doing stuff that takes too long on the UI thread. And so one of the very important things that we decided we wanted to do was make sure that we created responsiveness in the system. And so we called that WinRT. Choice number 1, non-reentrancy. That's the OSTA. We'll talk about that. Choice number 2 was the thread pool that we talked about. Choice number 3 was async in a very large number of places. We'll cover that in a little bit. And choice number 4 was no arbitrary HWind creation. So windows only come about as a result of contract activations. And then we brought two existing well-known UI frameworks to the system. So once you have this, what do you have to do? You have to tie the following elements together in your system. So you have to be able to create windows. You have to be able to manage the event and the message flow in that. You have to be able to get work queued onto UI threads. You have to be able to make calls in and out of those UI threads. And then you have to be able to handle input. And so the next little bit on this talk talks about how we tie all of these together. Oh, and you have to prioritize this with respect to each other. And there's another interesting set of problems in those which we won't go quite as deeply into. The entity that ties these together is ASTA. And you'll forgive us, one of those A's actually does mean apartment, but don't worry about it, just call it ASTA. It's the UI context in WinRT. So once you get one of these contract activations, and one of those is click a tile and you get a full screen app up, that's the thing. You'll get a window, you'll get a thread, and you'll get a dispatcher associated with that thread. So this is the main UI thread. It turns out that the main thread of a WinRT app is actually another thread, which we call MTA. So there's a main and a thing. But this is a detail you don't have to worry about. There's still a main UI thread in these apps. These OSTAs are non-reentrant, which means an outgoing call is progress and an incoming call blocks. And so if you're making background work, it's very, very important that you either deal with the fact that if you call straight into a UI object in WinRT that it may block, or you should dispatch work to it. So the other part of that was please do not make an API service that has lots of synchronous API calls. And so we scoured all of the APIs that were being built in the Windows 8 and 8.1 timeframe, and we reviewed them all. And one of the review points was, does that method execute longer than a very small number in the tens of milliseconds? The answer was potentially yes. That method must be async. And so you will see lots and lots and lots of async across the platform. So as you've played with the new system, I think you've noticed that there are many, many fewer instances of spinning donuts and hanging apps on the system. And that's due mainly to the fact of async and some other things we'll talk about briefly. I'm going to go through these slides quickly because in my infinite wisdom, I booked 50 slides into 60 minutes, and it's some pretty deep topics. So when async operations are hot start, that means when you call an async method and it returns an async operation for you, it's already running. And then you attach a completion handler so you know when it's completed. And one of the details there is it may immediately fire back to you that says, I'm done. Right? Some of these operations, which are designed to be async, actually may complete quickly. The reason they're async is they may not complete quickly and they take time, and we don't want to hang the UI. So when an async operation completes, it's in one of three states. I completed with a result, good. I canceled because you asked me to. Cancellation is a user request in the system. Or the third thing is it terminated in an error, and then there's some sort of error code. These async operations are one-way state machines. They go from being produced in a running state to a completion, and then there's a closed state when all of the resources are scavenged out of it. But it's a one-way state machine. So the model is very, very simple. They're running, you put a completion, you get a completion, and that's done. And obviously, there's no such thing as an async operation that's running on the UI thread. So every one of these things actually run on the background threads, typically the thread pool. One thing is if you have to study this pattern, look at async.h and WRL. Every detail of the pattern is clearly documented in this file. If you have to produce async objects, please use a projection or that file. Do not try to create yet another one of these things. Since I designed the async and implemented many of these objects, I know for sure you will get it wrong. And that's because I got it wrong and wrong and wrong and wrong and wrong and wrong until we eventually got all the, the bugs out of the system and did it. But the good news is you don't have to, PPL can produce async objects. You can use WRL to create these things, and they will fully comply with the pattern of the system. The point of this slide is that the async operations are agile. And if you think about it, it's pretty obvious. You want them to be agile because you want them to be directly callable from UI threads. So that's the whole point of the system is you want UI to be able to create these operations and get the result of them back. And so they're one of the very prominent reasons why we created this agility facility in the system. The async support is in C++ with PPL. PPL existed before the Windows runtime. Its primary job in life was to maximize CPU utilization. We're actually using it for the opposite. Like anything that consumes async on this is mainly targeted at responsiveness. We want the UI to be responsive. When the user puts their finger down on the tablet and moves it around, we want that feedback to be immediate. Responsiveness is really the key. And so maybe one day we will get into the idea of how do we saturate these CPUs and use these patterns so we can get maximum utilization of the machine. But actually, we're actually in a completely opposite world here, which is we want responsiveness and we want to make sure that we don't use up the battery. And so it's almost the opposite of saturating cores, is we want to use the cores as efficiently and as little as possible. Once you do this async, they start on a background thread, and you might do a series of operations. And a series of operations, you might open a file, you might do a bunch of reads out of them, and then you might get the result of those reads back to a UI thread, maybe display some text on the screen. The point of this slide is that you're starting on a background thread. You want to set up the context in PPL so that you continue to run on the background thread, which is task continuation use arbitrary, until the last one is done and you're updating the UI, and then you either want to do a core window dispatcher call or you want to just get back onto that originating context. So this thing about debouncing is stay on the background thread until the end. So one of the things that is associated with the window is the dispatcher. And this is the central mechanism in the system. It is your basic UI processing loop, and it deals with ingoing and outgoing calls. It deals with window message processing, and it deals with the dispatch. Oh, I'm sorry, and the last thing is input. And so it has to deal with all of these various kinds of workload. The dispatcher itself has 4 priorities. And so normal is everybody runs together. Low means input beats the dispatcher. Idle means everybody beats the dispatcher. And so I'm sorry, these are when you create a work item for the dispatcher, this is one of the arguments. And high means, well, our documentation says don't do that. And I'll tell you what that really means in a second. This slide is really what I referred to earlier. It's like in the 95 time range when, Win32 and everything, the modern set of apps, when the original Photoshop was built, you had one message loop. You did everything on that message loop. It doesn't look like that anymore. I mean, I think every one of you who has dealt with UI now and animations and flows realize that everything's tied to the frame rate now. You have a 60 millisecond frame rate. You have a 16 2/3 millisecond paint beat that runs on that application. And there's certain things that you must get done before that vsync happens. And so, in one version of that system, it's just like, okay, I'm a slave to the paint beat. But actually, that's not actually how it works, because you have separate render threads now, and you have separate composition threads. And so the point of this is that the way that you design these systems isn't about message processing. It isn't about frame rate. It's actually just about responsiveness. You want to tailor the system so that critical layout changes occur quickly and that you're responsive to input. And that's actually the main job of writing UI now, is to get these things. Because what do you do on the UI thread that's threadifying? You're usually just doing one of two things. You're either doing an initial layout, you're either doing a really big change to the layout like a navigation, or you're making little tweaks. When you put text in a text box, that's fast and a small tweak to an existing layout. And so it turns out that the kinds of things you have to do on a UI thread typically now, if your application is designed correctly, are fast. The only thing that isn't fast is layout changes. And so you have two jobs in life there, basically. One is to get that layout change done quickly. That must beat the paint beat or the vsync, because you can't render anything until the layout is done well enough to be able to be presented. Or if you can't possibly do that, which is very, very common, then you need an animation to soak up the time in between while you're getting that thing. The nice thing about it is our systems have independent animations which don't run on the UI thread. And so there's a way out of that conundrum. Okay, so I promised to tell you about high priority in the dispatcher. We use it for two purposes in the system that I'm aware of. So the HTML, CSS, Windows web app infrastructure runs on something we call WinJS. And it uses high priority for layout changes. And so it tries to get the layout changes done quickly. The core application object actually supports suspend, which is a state that applications get into, and there's a time limit on suspend. Once an application gets a suspend notification, there's a short amount of time to do housekeeping and then get ready to be suspended. We deliver that with high priority. So high priority in the dispatcher is a very, very sharp knife. It will get your work run immediately, but be very careful what you use it for, because you will block out other critical pieces of the system. And so now you kind of know exactly what that is that you're competing against. So if I were writing an app, I would never use high. But in case you have a need for it, this is a view into what happens in the system when you use that. So I think the most important message here is the one that I gave before, is that using async gives you the ability to get a lot of work off of the UI thread. Then you have basically the job of getting your work done on the background threads, dispatching the work back to the UI thread, and then making sure that you get layout changes done quickly. The other thing is like when you're doing work on your background threads, and you're thinking about battery life, the very nicest thing you can do to the system seems to be, well, I'll just try to run as much as I can at idle. Like I'll let the system do anything and I'll run when I can. Actually, even better than idle is no work at all. So when you're thinking about batched mode on your app, what we don't want to see when we're looking at a CPU perf utilization of your app is this. Like it's running continuously at a certain level. Even if that certain level is low, you're keeping CPUs and cores and caches and everything spun up in the system. Even better is no work, no work, no work, no work, burst, of work, no work, no work, no work, no work, no work. It turns out that when we do wattage and battery utilization, that's the best workload of all. So it's a really interesting new world now. This is like when you're dealing with all of these mobile form factors with batteries that users care about the life on, the things the way that you factor your code and the responsibilities you have, I think is really different than it was 10 years ago. And it's because you didn't really have to worry about these problems. Everything was created to run continuously. And so that's not the case anymore. And so, especially if you have legacy assets, think about how you can create these in terms of work units, and also think about how you can create those units to be bursty so you can keep the CPU and the GPU as loaded as episodically as possible. This says to use the dispatcher. I'm going to run through this last slide quickly. Last slide. We're making a bunch of investments in async. I mean, so now you understand why async is so important to the platform. It's like it's really important for the battery life. It's really important for the responsiveness of the system, et cetera. Unfortunately, a continuation in a .then kind of world creates some challenges in programming. Herb Sutter gave a talk at Build 2013. I love the 2 minutes in here where he introduces async. I recommend you go look at this. I mean, this is the C++ geek part of the talk, where he says, in a continuation .then kind of world, what does it look like when you try to merge that style of programming with a for loop? It's fascinating. And just as a little bit of cheater on the thing, please watch it. It's fascinating is Herb couldn't even write this code. Like, I mean, he didn't try for hours and hours and hours, but Herb tried for how long?
I didn't even want to know if it compiled.
Yeah, exactly. It was so hard to write that code. Now, there are ways around this problem. You can restructure the code, do this, but you have to really think about it. C# brought await in the Windows 8 timeframe. You write await on some async method, and then you write some code after it, and it just looks like synchronous code that you wrote 10, 15 years ago. But the magic is the statements following the await only run when the completion happens. But it's like your kids, if you have them, can write the for loop with await. Nobody in the room practically can write the for loop in a continuation in .then. And so the talk I most want to see today is Dion's talk this afternoon about await. And so I'm really excited that we're bringing this to the platform in the language. So that's it. I'm actually 2 minutes over, but fortunately we have time for questions at the end of the day, and I'll be here. So I hope that was a good walkthrough of threading in Windows and what the system looks like today. Thank you very much.
Thank you.